Hello, Houston. You are now through with the agony of the second exam of 3 that will be given during the course. Just as a quick review for you, we're going to give you both the third exam and the final at the time of the final. Each of them will be 1-hour exams, just like the 2 that you've already had. And so the 3-hour final exam period we've got, that won't begin to crowd you in terms of time. You should have plenty of time to do both the exam covering the last third of the course and then the final, which will cover everything. About that deep, but it'll cover everything. So in any case, today what we're going to move into is a discussion of problem solving and eventually creativity. At least, to the extent that we show creativity when we're in problem solving. And I will confess to you that this is going to be one interesting lecture for me to deliver to you today, because it's going to either run about 30 minutes or about an hour and a half, and I'm not quite sure which it's going to be, because I've got a lot of thinking time reserved for you in here. So I want you to think of putting your I don't want you to think of it. I want you to put your thinking caps on, because what I'm going to do is pose to you some of the problems that have traditionally been studied by psychologists in various activities related to language, thinking, and problem solving. And we're going to look at some of the strategies that can be used in solving problems. But the array of problems, it was fun to kind of go across the literature and pick out some of the more interesting studies that have been done on various kinds of problems. So I'll share some of those with you as we go. So in essence, problem solving is really required essentially any time. We can diagram it in the following way. If there is an individual, problem solving is basically required any time that his or her goal-directed activity is hindered. So if you're trying to get to a goal and some kind of an obstacle prevails or stands between you and the end state, whatever that may be, the net result is likely to be problem solving. And so what you're facing there is the idea that we're taught in a variety of ways how to solve those problems. But if you think about where it comes from, it actually tracks all the way back to the frustration that is engendered by that kind of a situation. And so basically, if we define a frustration, we can actually define it in any of several ways. You can define it as an intervening variable. That is something that you and I never actually see. And in that case, we're talking about the state of the individual in a frustrating situation where problem solving has been blocked or hindered in some way. That would be looking at it as an internal state. And that would be expressed in the following kind of situation, where somebody says to you, essentially, I am wrought up by my inability to communicate with him. I cannot make him understand, and it makes me feel very badly. You think back to the book on communication between men and women that we were talking about in the previous section, and in one sense, the internal frustration any of us may feel in certain situations. Deborah Tannen's work would be reflective of that kind of frustration. So in any case, frustration may be an intervening variable, but there's another way to talk about it, and that is instead to talk about it in terms of the independent variable, in which we talk about the state of the individual in a situation in which strong motives are perceived to be blocked. That makes it the independent variable, essentially the cause. And in this case, we could illustrate something like, I was frustrated by my attempts to reach school by the snow. Well, for you and I in Houston, snow typically doesn't get quite that deep, but certainly water does. So we might, in that kind of an example, talk about I was frustrated in my attempts to reach school by the water, by the rising water, indeed by the floods. And in the last 3 years or so, we have had an amazing array of having ability, I should say, to have fairly deep puddle thunderstorms occur the night of the cognitive exam. So you might want to think about getting here a little early for the final exam, just to make sure that we don't have another drenching rainstorm that comes, and people have sometimes had to make it up the following semester, which is always an option. So in any case, there's a third way to look at frustration, and that is instead to look at the consequences of it, define it as the dependent variable, in which case we're talking about problem-solving behavior is abandoned. And in that case, we see it in ball season, okay? Whether football or basketball or softball, hardball, baseball players that we're talking about. It was obvious he was frustrated because he was perspiring and red in the face, and he was no longer thinking logically. We've all seen examples of that on the sports fields, whether male or female, in a variety of different situations. And so essentially, frustration is certainly going to lead us into the need for problem solving, But don't use that word too lightly. What I'm really suggesting here with the different colors I've used in the definition is to point out that actually when frustration is used as a word and defined as a concept, and defined as in the definition that's used there, parts of it can be used as an independent and intervening or a dependent variable. Okay? Any of those are potentially possible. The state of the individual in a situation in which strong motives are perceived to be blocked and problem-solving behavior is abandoned is frustrating. Net result. What that leads us into then is problem solving. And one of two kinds of problem solving is going to have to be involved here. Okay? One of them is essentially trying to figure out how to get around the goal object, the frustration I mean, and in the other case, it's going to be going through it, which can happen. You can simply overcome the nature of the objection, in the frustration that you're experiencing in a particular way. If you think about it, we're actually taught problem solving in a wide variety of college courses. If you pick any, the nature of the problem varies really as widely as the sciences, but all of those sciences share in common the constructive attitude toward problem solving. That is, that's basically what science is about, is picking out a particular issue or something, studying it, and resolving whatever misunderstanding or lack of understanding exists in a given situation. So regardless of the science, what the labs really are oriented toward is teaching skills with which to overcome the challenges of the discipline. Well, it isn't really the discipline, it's the subject matter of the discipline. That's what's really being taught in a methods course. And if you think about our own psychology undergraduate curriculum, one of the key lower level required courses is 2301, Methods and Data in Psychology. Methods is the key element there, and really what's involved in that course, as you know, since you should already have had it as a requirement for this course, a prerequisite for this course, is that it's teaching you problem solving, essentially specifically around psychological designs that will work and the techniques that are used to isolate variables and begin to understand what their effect is. And that's functionally problem solving. A methods course is essentially formalized instruction in problem solving. But as you know, depending on whether you're clinical or social or developmental in your orientation, the kind of problems that we encounter vary quite widely. The underlying issue here is basically, can we learn from one problem-solving situation skills that can be transferred from that into other or similar situations? That's one of the issues that the solvers of problems are trying to study. Are the skills generalizable from any given situation to other situations where another problem is encountered? So the problems of debated similarity of problems by psychologists have led to really the need to classify various kinds of problems. That is, the debate as to whether the problems are comparable or not has led some degree of effort to be poured into essentially looking at how do we actually organize the problems that we end up tackling in this discipline. And so basically, Greeno actually suggested three broad classes of problem-solving situations. The first of which, and it's going to take us most of the program to get all three of them in the variety of things I'll be showing you here. Excuse me. But in essence, one of the types of problems that he defined are what are called arrangement problems. Arrangement problems represent essentially an unsolved condition that requires elements to be sorted or viewed in a new or unique manner to satisfy a specified criterion, that is, whatever the desired solution is. And so there may be an end state, there may be a which is desired, even though it's not obvious at the time. But the goal is to take the presented elements and arrange them in a new way, rearrange them essentially, and that's so the problem is solved when the correct arrangement has been established. Many orders may be possible if you're given a variety of stimuli, and the question is, how long does it take you to come up with what turns out to be the correct identification? Only one of them typically satisfies the demands of the problem itself. One example of that is grammar. Well, that's actually not correct. Wait a minute. Let's try it. Not that way, but monogra. No, that isn't it either. Hang on a second. System's giving me trouble this morning. Garraman. No. No. let's try anagram problems. Okay? That's one of the more basic types of problems that can be utilized. And in essence, when we define an anagram, we're defining it simply as an activity that involves exactly what I just went through there with pre-planned fakes. But in essence, an anagram is essentially a puzzle that requires rearranging a limited number of supplied letters to form a word. It's nothing more than problem solving, identifying particular words. And as you can understand, there are a lot of different possibilities. In your book there, I have, for instance, posed the following to you. Okay? What word can be made out of 2 A's, 4 S's, an N, and an I? Don't do it publicly, but simply raise your hand when you know what the answer is, and I'll simply give you the time to work it out. Okay, we've got 1 that knows the answer. 2, 3, 2.5 maybe. 4. Takes a while. What is the word? Now you can get on mic. Just push it and talk. Then just belt it out to me and I will report it. What is the answer you've come up with?
Assassin.
Assassin, yes, exactly. Got another one for you. This one's a little trickier in a different way. How about no south? How many of you come up with an alternate solution to that? No south leads to or can be respelled as what word? And you will be surprised when you see the answer here, when you finally reach it. Okay, 2 have suddenly come to insight. 3, 4. Okay, what is it in the back? Yeah.
Houston.
Yep, Houston. Now, one of the tricks that's buried into that is the fact that the T's, the no south, uses TH, which is a very high frequency letter sequence in English. And it may, in fact, bias your thinking. You'll have to think back to the way in which you solved it yourself. But that kind of a lead-in, a tease, tends to make us think only in terms of TH whatever kind of combinations as the potential solution in that particular situation, which of course doesn't turn out to be true, because in Houston, it's simply TH is not the order that's actually used. I will skip this one simply because I was teasing with it a little bit earlier, but that's one of the many different organizations that can be used about anagram. But then how about this one, Guinness? And we're giving you time at home so that you needn't scan through this. You can simply take the time to understand, review, or look at what you're doing as you try to come up with an English word associated with Guinness, involving each of the letters. Anybody got it yet? That one turns out to be tough because it involves some unusual letter sequences. Perfectly easy word once you see it. Anybody got it yet? Well, this will be a nice easy lecture. I'll just sit here and snooze. If you're having trouble here, they're probably having trouble at home too. Anybody? You have no insight at all as to how that actually is solved. That's what you're telling me. I even used the word. So sometimes the presentation technique can kind of mess you up. The next one, I don't know how to pronounce the lead-in, whether it's Sakusak, Sakusak, or Sachusak, I don't know. But what would you make out of that one? That one's actually a little easier. Anybody? This is one of the problems when you tape early in the day. Bingo. Yes. Okay. 91 F's and an A. Or how about this one? This is my favorite, actually. Einsteruvi. It's such a beautiful pronunciation. But what's the word that's buried in those letters? This will be the last one I tease you with. Yeah. Yep. It is university. So see, once you get through it, then you'll understand how to do that. So in essence, when you look at that kind of a problem, anagram problems, people have actually studied that specific subtype of problem and identified several different things that actually contribute or feed into our ability to solve that kind of a problem. One of which turns out to be fluency in generating possibilities. Okay, fluency in generating possibilities is one of the things that facilitates solving of anagram problems. It's best in solving those kind of problems basically to generate partial solutions and discard those that are really unlikely to be fruitful. For anagrams, for instance, knowledge of letter sequence, letter orders is highly desirable. You didn't, in any of those, the posings that I gave to you, G and H, well, the example that I used with no south, meaning Houston, or rearranged into Houston, is an example of where a prominent letter sequence, TH, which is a big deal in our language, it's used a lot, misleads you in solving that, because in that particular word, Houston, the two letters are used very differently and independently of one another. But a general knowledge of TH as a good example, RE as another example, high frequency, makes it easier to pull together subunits of the stimulus materials and try to organize them into whatever turns out to be the correct answer in a given situation. So basically your familiarity with ability to generate possibilities is one of the keys to learning how to solve these problems. A second is essentially retrieval of solution patterns. That's kind of a high-level version of the previous thing that I gave you there. And that is the ability to retrieve possible words from long-term storage should aid in recall. This is essentially a metacognitive skill where you're thinking about your overall vocabulary in the context, reviewing your vocabulary in the context of looking at whatever the stimuli are that you've been presented with. For instance, no south as the highly misleading example there. But essentially your skill at being able to kind of scan across your vocabulary and pull out possible candidates that use, for instance, only the letters within the sequence may lead you into, for instance, sight. In one of the last ones we did, insight as the final example. Sight might be one of the words that you would come up with, which then makes the problem solving a lot easier since insight was the actual answer. But that ability to retrieve partial solutions from your memory is a second skill that will contribute to problem solving in anagrams. And thirdly then, knowledge of the principles that constrain the search are also very frequent. Knowledge of letter frequency helps a great deal. And in fact, tying back to something we've talked about earlier in the course, the disadvantage of no south as the stimulus term actually is semantic priming. Because what happens is south is such a tightly integrated letter, and we in the south tend to use that word a lot. So SOUTH is a tightly knit sequence, and it doesn't occur to you immediately to separate that out into Houston. But these are problems where insight may be valuable, as we'll discuss more a little bit later in this sequence. But the ability to generate words is the third example. In essence, what I'm talking about here is that you're drawing predominantly from the words and the units of meaning as a good basis for pulling together the parts that you need to solve an anagram. There's a second type of problem that we can also talk about, and that is what are called organizational problems. And these take a very different form of arrangement. And I apologize here because I have a couple of really nice examples, but I did not have time to assemble the materials that I needed. But we can talk about them, and at least one of them I can diagram for you. One of the classic examples of this, and this is the skill that I hope we're engendering in you today. I found this picture, and it's such a neat parallel between Rodin's The Thinker and the person below, people below. that I just found that kind of intuitively interesting and a good thing to drop in this particular case. But in any case, what the organizational problems do is really force you to do a lot of thinking about the very limited tools or elements that you're normally asked to, or provided in order to solve it. And one good example of that is, for instance, what's called the candle problem. It's done by Dunker way back in 1945. And in essence, what you're asked to do is to mount a candle on the wall vertically so that it will burn until it runs out of wick without singeing the wall. And the only thing that you're given is a candle, a box of matches, thumbtacks, and string. That's all. And the question is, can you figure out a way to actually mount the candle in such a way that it will burn to the bottom of its wick without putting any singe mark on the wall? And that turns out to be a classic problem. It goes all the way back to 1945 when Dunker originally developed this. But the problem can be studied and has been looked at in a variety of different ways. One of the more difficult ways in which to present it to people, leading to less immediate solutions, is to emphasize, for instance, the string, which is actually there as a distractor. It doesn't have anything to do with the most obvious solution to the problem itself. It turns out the box of matches which is there is actually, I started to bring another combination of things, but what you could do instead is to use a box of thumbtacks. But in both cases, if it's a box of matches or a box of thumbtacks, the net result is that you and I, people studying that problem, trying to solve it, don't tend to think of the box as independent of that which it's wrapped around. And so it turns out that one of the ways to aid people's solution to that problem is to give them the box separate from the matches that were held in it, or from the thumbtacks, if that's what it was used for. So simply separating the box from that which it contains is a very substantial cue to people to think about the box itself. Particularly, for instance, if you know the kind of matchbox that has it's a slide-out tray, 4 vertical sides with a bottom, and then it's a second thing that's wrapped around it, so you push on one end to slide it out, and that becomes a platform. So essentially, particularly if you have the box already disassembled, the box, the top, or not even the top, just the bottom, if it's tipped upside down, so you've got the match box there, but the matches are separately on the counter, that also tends to lead to faster solution. Because what's happened is that you've given more elements in the proper element in which they need to be utilized. And again, it's just a matter of how substantial the cues are, how substantive the cues are that you're giving to people. And ultimately that problem, if you've never actually seen it solved, is solved simply by taking the matchbox upside down, putting thumbtacks underneath it, and pushing it against the board that way. So you're putting the thumbtacks through the bottom of a matchbox, which comes up, flat surface, and then drops on the other edge. And the net solution is then that you just light the candle, the matches were used, and the candle, and simply tip it so that a little bit of wax falls on the top of the matchbox, and then very carefully you can center the candle on the matchbox bottom itself. But it's not immediately obvious because we don't tend to think of either thumbtack boxes or matchboxes as platforms, but that is exactly what allows that particular problem to be solved. My very favorite problem in this sequence is what's called the string problem, and I was going to do that in the studio today, but it turns out this is one of those problems that if you've not seen it solved, it is very unlikely in the length of time we have in a television lecture that you're going to be able to solve it. And in essence, the key element in this particular problem is that what you've got are essentially 2 strings. And so we've created 2 I-beams here that we're going to utilize on the screen. And in essence, what we're going to do is essentially attach a string. Notice I've tied a very careful knot at the top. The string is hanging off the ceiling, we'll say. And then I'm going to put a second string way over here. Same length, same constitution, and so forth. And in essence, your challenge is to tie those 2 strings together. And they have been very carefully positioned so that if you actually get in there, I am at my artistic best here, okay? Tolerate this as being you in this. Roll with me on this. Give me a little liberty here. Oops, I didn't do everything I was supposed to. This line is not supposed to be there for a minute. But in essence, they're tied in such a way that it is not possible to take one string, pull it all the way out to the end, and stretch and grab the other string. That's not going to work. Okay, and that's the problem, really, is how do you in fact get possession of the second string. So in essence, we can't do it that way. The only other thing that's available, and you can in fact put, the one thing you can't do is put additional string, because somebody would ultimately come up with the idea of tying string to a string to increase its length and then pull it over. That would work. So we don't give additional string. But what's normally there is a tool, whether it's a pair of pliers or a scissors or a screwdriver, anything like that, will also be in the general environment when the problem has been posed. And the key, the way to solve this, does anybody know, how many of you know the answer to this particular problem? Oh, see, I should have brought it in today and set it up for you. Okay, well, let's think about that a minute. What do? You've got everything you need to solve the problem there. And in fact, I'll give you the one hint, the thing which in the circumstance of the problem actually increases the likelihood that it will be solved, is that if the experimenter walks past either of the strings and, you know, maybe incidentally catches it on his or her shoulder and kind of drags it along so that after it falls off the shoulder, it swings. That provides the solution. In essence, it increases the odds that people will discover the solution, because the solution to the problem, has anybody got it now? Very easy. Okay, whoops, that wasn't supposed to be there. You take the screwdriver and attach it to the string, set the one string swinging on a pendulum format, and then you can simply go over to the other string. Love this art. Ta-dam. We could actually solve it. But the key there is, sorry that frustration got back in there. Maybe that's what people would experience in this situation. But the key in that is realizing that that screwdriver or the other tool, whatever is the weight, can be utilized to tie to the one string, set it in pendulum motion, and then you can push it away from yourself, and in the time that it takes to swing back and forth, you can walk over and grab the other string and pull it too, and then unhook the screwdriver and tie the two strings together. I've always liked that because it's so counterintuitive. It's very easy to solve once you know how to do it. But it just does not strike people when they see two strings hanging 10 feet apart when the strings are only about 6 feet long as to how to go about doing that. So we'll destroy the apparatus here now for you. But the string problem actually leads into a discussion of functional fixedness, which is one of the things that we tend to I could mention that either in the context of the candle problem or of the string problem, because in both cases you really have to break free from functional fixedness, which we'll come back and talk about later as a completely separate element. But it has to do with the limits that you and I tend to impose on ourselves when we're trying to solve a problem. And in both of these cases, solving the candle problem and the string problem, elements of the environment have to be used in an unusual way. That is, in the string problem, you have to envision the matchbox being upside down, and upside down, thumbtacked to a wall. It's a perfectly good platform, but people don't don't tend to think of it because they've never seen it used that way. And in the instance of a screwdriver, or even a pair of scissors or something like that, we tend to think of it in terms of twisting a screw into the wall or prying something. We don't tend to think of it as a weight. But that's what's really dependent on the solution of the problem. That's what the solution of the problem depends on, is what I should say. Now I've got another one for you, and this is a real intellectual mind bender, okay? And that's what's called the alter window phenomenon. And this one, I don't know how somebody thought of this. People stay up nights creating these disasters for us, I'm sure. But in essence, what we're going to do is to paint a surround on a cathedral window. And the window itself is round. Therein lies the problem. But in essence, what we're going to do is to paint a golden pattern above and below the window to try to accentuate it a little bit. Okay, it's to be decorated with gold leaf paint. The area to be decorated is bounded, and these are critical to the information needed to solve the problem. That area is bounded, first of all, by two parallel lines, which I've added to the picture. It's a little hard to see the black against the dark blue background. I apologize for that. But in any case, the area to be decorated is bound by these two parallel vertical lines. The lines are tangential to the circle, as indicated in the drawing here, and they're the same length as the diameter of the circle. Now what we're going to add is the wrinkle, and that is these lines are joined top and bottom by semicircles. As you can see, I've simply added that in the diagram there. And there's the problem. How much paint should you buy? We're using gold leaf, and this is a church we're working for, so it's very important not to use a drop more than you have to, because then you have to pay for the gold. So the question is, how do you figure out how much paint to buy? What is the square footage that's to be used there? The deathly silence in the studio suggests that we've in fact created another problem. And that is the essence of what problem solving is all about. Think about it though, because you have available to you all of the information you need to solve that problem. Go ahead, get on the mic and give it a shot. Kind of work through what you're doing or the statements on which you're basing the solution.
Okay, this is totally kind of a guess. But because he has the vertical lines are the same length as the diameter, so you know how long they are.
Yeah.
And then you cross them to each other, like on top to make a square or a rectangle.
Okay.
Because they should be the same length as the diameter of the circle.
Yeah, so you could move the left or the right line up and the other one down so that they're parallel to the floor instead of vertical.
Well,
what you're suggesting.
yeah, it'll make like a square.
Okay.
And so you can figure out how much is in the square, and then the semicircles that are left is equal to the circle inside. Yeah? No?
Yes, but you've left out one step, and that is that what you've defined very accurately the way in which to calculate the area of the circle itself. But the one thing you didn't mention, which was implicit in what you said but not actually mentioned, was the idea that what you need to do is subtract the circle from the square to get those goofy areas, because what you've got essentially are corners. The real tricky area in this particular figure is right down here from the line that she described putting across. You've got these kind of amorphous, well, they're not amorphous, they're square on two sides and round on the other one. Well, it turns out that what's actually involved there is that the solution to that is essentially the fact that we can calculate the area of the circle simply because we know the diameter. The areas of the semicircles essentially is half of the total circle, but how about the area of the four funny-shaped remainders? And that's the problem. That's the crucial element of it. And to do that, what you have to do is simply, as she did, come to the realization that there is in fact a square that can be created of known dimensions, the same size as the circle. And then since we use semicircles at the top and the bottom, you can actually put those semicircles together and recreate the circle itself. And then to figure out the remaining paint area, all you have to do is subtract the circle from the square created by moving those two vertical lines originally. Okay, so that you end up with, it turns out, a very precise way to calculate. What you do essentially is to buy a square worth of paint, because what you've got are two semicircles and the remaining area, which fills in the square. So all you need to do is buy enough paint to cover the square that was created or implied by the initial vertical lines that were added on each side. So what tends to happen there is the distraction is those funny areas, and some stress is put on that you want to make sure you don't waste any paint and so forth. But those funny areas actually complete a square, and that total area is really what you have to paint. Wertheimer, one of the classic Gestalt psychologists, worried about that kind of problem, and he identified basically two different types of thinking that tends to be typified in this kind of a problem-solving situation. Okay, so again, I guess I didn't show you the final word here. The golden part, that's as close as PowerPoint would get to gold, but the yellow part there is what you needed to paint. And you now know the answer to that particular problem. But in essence, in terms of how we solve that, Wertheimer identified two different types of thinking that can limit your way to handle this. One of them is what's called thinking which is structurally blind. That is, you reproduce thinking that's used in other situations when it's inappropriate to the newer situation. That's one type where you're structurally blind. And the other type that tends to lead to a solution to the problem is what's called productive thinking, which is essentially showing sensitivity to the structural requirements of the existing problem in that situation. So if you have a grasp of the general principles applied, that will facilitate your ability to solve the problem. Let's look at another type of problem. And these are what are called insight problems. And we'll define insight simply as the sudden discovery of a solution following a period of unsuccessful attempts to solve a problem. There's a classic study that I won't be talking about in here, but I want to set you up to envision what I'm going to be talking about here with the following. Actually, it was an animal study in mind, and it goes all the way back to Kohler and the history in terms of which the problem was created and ultimately why it was conducted, was that a number of German scientists escaped from Germany as the Nazis took over the country, and being of Jewish persuasion, they ended up needing to get out, being forced out of the country. They went down off the coast of Africa. If I remember correctly, the island was Tenerife, off the coast of Africa. It turned out that those very fertile minds worked in a number of different areas related to, among other things, studying chimps. There was a big study of, or a big stock of monkeys on the island there. And one of the classic problems that came out of that was the early predecessors of trial and error learning. And the problem that they actually used was to establish a box for a chimp. And in that case, the initial problem that they posed to the chimp had a banana. I mean, it was a cruel problem, but the box had bars in it, and there was a banana, all peeled, ready to go, out on the ground. The only thing that was in the box were sticks that would fit within themselves, kind of like if you're erecting a flagpole where you can put one stick inside another, so that the sticks were there, but they were disassembled. There were just 3 sticks. It turns out if you stuck the stick within each other, you could end up taking the 2-foot pieces and end up with a 6-foot probe. And sure enough, eventually, the monkey, a lot of frustration in that. Talk about being blocked about getting to a goal object. There was a lot of frustration exhibited there. But eventually, what they tended to describe would happen is that the monkeys would sit down, and all of a sudden they would get up in a typical solution and walk over and grab the sticks, or in some cases they had been playing with the sticks, but as soon as they discovered the fact that the one stick would fit into the next one, very, very quickly the second one was put in, and then they were there using the stick to pull the banana in toward them, which in that case was the solution to the problem. It was out of that series of studies that the whole concept of insight was developed in Gestalt psychology. That was a major founding point of insight as an explanation for what's going on. Learning theorists, and here is the one place where I'm not going to be able to give you the reference. I'll try to look it up and perhaps mention it at the beginning of the next program. But somebody actually took that initial idea of trial and error learning and the arrival of insight and essentially created a series of some 600 studies in which they would put a cat or an animal in a box, and in the case, the goal was to escape the box, in that case, to get to food. The way they set the thing up was such that the animal could learn to step on a pad, which would in fact release the gate so they could get out, or there'd be a string they had to pull or something they had to bite. There were just a zillion different combinations, 600 actual ways in which they eventually presented the cat with the animal. And it turned out that if you plotted the speed with which the problem was solved, in each case what they did was give the animal the problem, and they measured how long it took to solve it 6 times over. And what they found in the early problems, the first 25 to 50 studies, problems I should say, in the whole study was 600 problems long, but if you plotted the reaction time across the 6 trials, there was very little improvement from one trial to the next. But gradually what began to happen is the curve dropped, so that what would eventually happen is that the length of time to solve the first problem was still substantial, but as soon as that problem was solved, when it was presented to them again, the reaction time was essentially as fast as the response could be made. And so in that case, if you look at it in terms of the initial solution of the problem, what the learning theorists were arguing was that insight is simply a problem-solving strategy that develops over time. So that when you then look at the problem, first time it's presented, yeah, it takes a while, but the next time it's solved instantly, or very, very rapidly. So that significant drop in reaction time was cited by the learning theorists as an alternate explanation for insight. So kind of keep that bias in mind as I'm going through several different examples of studies that present insight kinds of solutions or potential to you. One of them is this, and I love this one. It doesn't relate at all to the other triangle problem that we were related, and I hope I don't bias you in that way. The challenge to you is, with this highly triangulated structure, what is the minimum number of dots that you can move so as to convert that into a triangle standing on its point instead of its base. In other words, how do you convert the triangle so that it's resting on its point, the appointed corner, instead of the flat corner? Instead of rating on its base, or standing on its base, it has to stand on its point. Okay, one person has got the solution. Two, it looks very complex, impossible. A zillion rearrangements. Doesn't turn out to be true. The key is, again, to conceptualize the dots individually relative to the whole. But in fact, if you think about this and generalize that hint, somebody has already gestured to me 3, which is the correct answer. You only have to move 3 dots in that situation, the corner dots. Because in essence, given the structure of the internal 7 dots here, all you have to do is move the 3 outside corners in this way, and the net result then is this. Okay, I should have let the system lay it out for you gradually as I had intended by design there. So in essence, you only have to move the 3 corner dots when it's resting on its base, given the relationship of each of the dots to the others, to put it on its point instead. That will tend to be solved, again, very rapidly. Once you make the initial decision or come to realization about what geographically you're doing when you move the one point, the solution tends to come very rapidly in that situation. But now let's look at another one. This one is a little tricky. Suppose you've got 12 gold links. And what I'm going to do is pose the following kind of problem to you. What I want you to do is make a bracelet out of, you're a jeweler in a poor country where gold is valuable, and you've got labor costs that are involved. So in this case, you've been given 4 links of 3 loops each of metal, gold. And the manufacturing costs are the following. If you break a link, it costs you 2 cents. If you solder a link together or do whatever they do to get links put back together after having been severed, it costs you 3 cents a link. And the question is, the challenge is, can you build a bracelet for not more than 15 cents? In other words, the 2 abilities that you're given there are to break links and to mend them. But there's a charge. Every time you do it, you have to pay some money, deducted off your total allowable gross manufacturing cost. Solution turns out to be pretty easy. And again, once you understand the element of solution, the rest of it follows very naturally. Anybody know the solution? Well, I'll give you a second just to ponder that before I show it to you. So again, the solution is to create a bracelet, either breaking or combining links, for a net cost of not more than 15 cents when the breaks cost 2 cents and the closing of a link costs 3. So obviously if you break a link and then reattach it to link other chain sequences together, it's a nickel a break. Nickel a break and rejoining. So what I'm going to suggest, the solution is basically the following. Okay? What we're going to do is to simply take the bottom link set of links and break all 3 of them. We're going to sever all 3 of them. And then we're going to take the chain elements and put them in this position. And then we're going to take the links that we just created this way. So if you sum it all up, what you've done is to break 3 links at a cost of 6 cents. And then you've also put those links back together. You've closed them. Again, 3 cents a link, that's a total of 9. And the net result then is that you've actually built a bracelet for 15 cents. And what it really comes down to is obviously the way in which it's got to be done is somehow when all they're allowing you to do is to break or to join, it's got to be solved by some kind of combination of breaking and joining. And it turns out you can do it for not less than 15 cents, but 15 cents anyway. So even the posing of the problem vagues it up a little bit for you. Not more than 15 cents implies that you can do it for less, but it turns out you can't. You've got to break enough links to hold it together. This one is my favorite, okay? The challenge here is to find the area of the square plus the strip. Productively, we ask ourselves, what general assertions do I know that apply here? And basically, there are several facts that I can give to you in this situation, okay? We know, for instance, that A is 6 inches. The A dimension is 6 inches. We also know that the B distance is 6.5 inches. And thus, what we also know is that the square determined by A squared, as implied here, is 36 inches. So the question is, can you find the area of the square plus the area of the strip? I've told you everything you need, but that's one where you really have to do some mental gymnastics to realize what is permitted given the problem that I posed to you. In that case, there are several steps that you need to go through to handle this, but it is feasible. The tricky part is, yeah, you can do the square, but you've still got to take account of this and this area, and in fact, the entire strip, because that's represented again. So then you start worrying about diagonals and how do I figure out how wide the strip is, and so forth and so on. It turns out you don't have to. Okay, you're overloaded with information here, and in fact, the solution is pretty easy. Notice what I'm going to do with one of the triangles. I'm simply going to, I can't do it smoothly in PowerPoint, but I'm simply going to move it up to point out that in fact the solution is pretty easy. And that is that you know they're actually rectangles, but the use of the word square repeatedly there actually misleads you. That's a case where the instructions, you have to move beyond the instructions in that situation. And moving moving one of the triangles allows you to realize that in fact you know the dimensions of the triangles. And all you have to do is figure out then that the triangle is, of course, 1/2 of A times B. So it's going to be 6 times 6.5, which gives you 39 as the area. And in fact, in that case, of course, the triangle formula is 1/2 of A plus B. So you've got half, but you then have to multiply by twice, because you've got two triangles of 18.5 inches each, 18.5 square inches. Net result is that the solution to that is 39 inches. And really, it's remarkably easy to achieve once you step back and think about it. Because I didn't prohibit you from moving the triangles, but I did give you very specific information about A and B and then the square that would result from A. But the square is a devious hint. It's a misleading hint. It's information you don't actually need to solve the problem in that case, and it will mislead people. What's realized, of course, is that you have to realize that the problem itself is really two triangles of A base by B height, and then position them in such a way that you can find out what the actual dimensions are. So structurally, blind thinking can sometimes generate an answer, even a correct one in some cases, without understanding why it is correct. And in that kind of a blind solution, it will not generalize well to other problems. So in many instances, the key to problem solving is actually understanding the system that you use by which to generate whatever turns out to be the correct answer in that situation. Let me pose to you a couple of other problems of the following type, and these are different kinds of insight problems that we're dealing with here, particularly numerical insight problems. For instance, can the following number be divided by 9? Now, of course, there are two ways to figure that out. One is to know the rule by which you can make that kind of an answer in any case, and the other is to simply 9 into 10 leaves 1, makes another 10, and 9 into that 10 leaves 1. So you can do the whole long division, but you may be aware of the fact, I mean, that's the long-handed way to do it, and the answer is yes. You can divide it by 9, you'll get an even number. But the easier rule to use, anytime you've got a number that needs to be divided by 9, you may or may not be aware of the fact that if you add the digits themselves, if the result is divisible by 9, then the number itself is divisible by 9. So even though you've got a monster long number like 1,000,000,008, it's almost beginning to sound like local taxes on the national budget here. But in essence, any number, the sum of the digits of which adds to a number that itself is divisible by 9 means that that number is divisible by 9. So in that case, we can very quickly and easily answer that problem. Gestaltists are interested in other problems. Let me pose one to you. For instance, you want to go to a club meeting on campus, but you're forgetful. In fact, you want to get to that meeting so that you can run for president. It's the debate club, you're good at it, you want to run for president of the debate club. You ask a friend to remind you when the club meets, because you know you're forgetful. You learn that the club has met. Why didn't your good friend tell you? And in fact, you later get an announcement that your friend has been nominated for president of the debate club. And so in essence, what's happened there is that there is an immediate revision of your rules for good friend. Because it's based, our concept of good friend is based on a series of principles that include the fact that good friends honor good friends' requests. That is, the good friend whom you asked to remind you of the meeting should in fact have done so. And the other thing is that good friends are reciprocally honest. Okay, sorry about the mispronunciation there. But you're honest with your friends, they are in fact honest with you. Can you think of anyone nationally whose reputation has been fundamentally altered, massively revised because of demonstrated lying? I can think of 2 examples. There's an athlete whom we have significantly revised our opinion of. At one time, he was a national leader, a star figure, a genuine athlete, a very gifted athlete. University of Southern California. Does anybody remember who I'm talking about? O.J. Simpson. And it turned out, you will remember, that he went through a very controversial lying trial, or trial where lying was pretty obviously going on because his wife was murdered. And that is a very interesting problem in terms of processing the evidence, because there's a very clear racial divide as to whether people view O.J. Simpson as guilty or not. But regardless of which way you go, it was very clear that he lied in some of what he said. And of course, there are enough vagaries in it that there's no way ultimately to work out this is what happened specifically. But the very fact that he was proven to have lied in a number of ways simply altered almost everybody's opinion of it. In that case, there's another who's undergone that kind of a change in cognitive appreciation. And that is, of course, the second President Bush. Now, it's interesting what the role of history will be in that case, and whether he will ultimately be simply analyzed as a fool, or simply very earnest and inept in applying the earnest principles, or what. But right now, given his recent stepping down from the office, his evaluation has dropped substantially. That can alter the information that you trust from someone and can alter the way in which you process problems. But in essence, one of the other things that we do in solving a problem then is to induce structure, okay? And in inducing structure, we can make it flexible in a variety of ways. That is, in the previous problems, the structure is in fact flexible. Anagrams, that's a good example. You can arrange the answer, the elements in a lot of different ways. In this task, as I'm going to give it to you, series completions, for instance, the task is, the structure is quite rigid. And your goal now is to discover what it is. So in series completion problems, you may be asked a question like, what is the next number in the series 1, 2, 3, 5, 8, and 13? What will the next number be in that series? And there is only one correct answer. So that's what I said. The structure is set. And as it turns out, so is the answer. Anybody know the answer? Well, I'll wait on this one. What is the next number? Need it on the microphone. We're having trouble with some of the equipment today. Yes, it is 21. And what's the rule by which you generate it?
Adding the number before it.
Got to be on the microphone or you don't get credit. Yeah, so you add 2, add the last 2 to get the next one. Okay, 1 plus 2 is 3, plus 2 is 5, plus 3 is 8, plus 5 is 13, plus 8 is 21, and so forth. Another one, what is the next number in this series? Be careful on this one, because this one is a little trickier. What is the next number in this sequence? This one is tough to do simply because there are a lot of steps in actually doing it. But the answer is starting with 1. First step you add 1, second step you add 1, third step you subtract 1, and then repeat the cycle. So 1 plus 1 is 2. Whoops, I have an error. I knew that. I did the thing wrong. This number should be 2 on the diagram. Okay? And so what the rule system is, the solution to the problem is correct. That should be plus 2. And so the step is, it's correct in my notes, and I didn't put it correctly in the PowerPoint. But add 1 gives you 2, add 2 gives you 4, subtract 1 gives you 3, start over again. Add 1 gives you 4, add 2 gives you 6, and so forth. How about this one? Now this one is subtle because it's almost identical to the other one, and yet you'll be surprised how different the answer is. This one is not a variation of the same rule redundantly applied. It is rather 2 different series that are integrated, if you look at it. Do you detect 2 different series going on? That is, one of the series involves 1 and 2, and then 3 and 4, and then 5 and 6, and that's simply add 1. And then skip to another series, which actually is 8, 6, 4. Okay? So in that case, what you're doing is simply, there are couplets of 2s, 1, 2, 3, 4, 5, 6, and so forth, and then a descending series involving subtracting 2. And so in fact, that's a self-limiting series. Very quickly you get to negative numbers, and that makes it even more obvious what's actually going on in that situation. But in essence, all 3 of those have only a specific correct answer that's involved. Or we can get into another very tricky kind of problem, and that is analogies, such as not anagrams, but analogies. These are used in tests of intelligence. They're used in the SAT, the Scholastic, the label of that have changed. I'll simply say the SAT, high school into college. They're also used in the graduate record exam, college into, or college into graduate school. And they are the only element that's tested in the Miller Analogies test, which is the single toughest test I ever took as a graduate student. A is to B as C is to D is the correct form of the answer. But what D may be is wildly different. Give you an example of one of the harder ones in a particular intelligence test from many years ago, and that is, given barn is to house, what word fills in the blank? Barn is to house as stall is to what? That's a classic analogy problem. Any guesses? I'll take guesses. Is it kitchen? I'm not budging. I'll sit here till the tape runs out if I have to. We'll pose that as a homework problem. Solve it by the next tape or you don't get credit. No, what is it? Let's have some guesses. Barn is to house as stall is to what? And you're doing what basically Sternberg analyzed as a series of steps. But what you have to do is work out the interrelationships that exist among those terms and cross different terms. So in that context, what is the relationship between barn and house? They're different structures, aren't they? And is a stall part of a house? No, it's part of a barn. But what relationship does stall have to barn that our unknown term would have to a house? What would you call a stall in a house? Bingo. Yeah, it's not a kitchen, because a stall operates as a dining room, as a bathroom, as a living room. It operates as everything. So the actual correct answer is to do as we've just done, and that is come up with room as the correct answer in that situation. I took a quickie test of intelligence many years ago. That is the only problem that I missed, and I was so bugged by that. I've been using it to teach with ever since. But it's really a very classy kind of illustration of analog problems. Now, my notes are a little jumbled here, but in essence, what I want to do is suggest that what Sternberg, I should say that correctly, has done is suggest that there are 4 elements that you and I go through in solving any particular problem. And I'm going to work through the next one and show you what he's talking about. And that is that he's talking about 4 processes. First of all, encoding. That is, we have to put the problem in words that we ourselves understand, so it has to be encoded. The second thing that we have to do is to make inferences about what the relationships are between each of those different terms. The third element that he's going to talk about is mapping. That is, we have to map the inferences that we've made onto the problem that we're trying to analyze or solve. And fourthly, then, we have to apply the information specifically to generate that 4th missing term in that case. So the problem that he actually talks about here is the following, and that is Washington is to Lincoln as 1 is to blank. And among the 4 steps that he identified then, as we look at that particular problem, the immediate solutions are pretty obvious, and that is it must be 5 or maybe it's 10. Because among all those things, Washington is the first president, he's also a general, and he's on the $1 bill. But then about Lincoln, we know that he was also president. He was a war hero, to many, not everybody, but to many. And he's also on the $5 bill. That might suggest or lead us in one direction. So in essence, what you're going to do here is take the 4 elements that Sternberg was talking about and do the following. First of all, we're going to encode it. And it was developed originally by Sternberg and Gardner and then applied in a variety of different ways. But he talks about encoding as simply identifying the important, relevant characteristics, as we just did in discussing the various features of Washington. Each of them is president, and so forth and so on. Secondly, we then engage in inference making or generating inferences. And in that case, what you're doing is establishing valid relationships between the first 2 terms. That is what we're looking at initially. What we start with is a discussion of the relationship between Washington and Lincoln. How do they relate to each other? Because that's going to allow us to predict the relationship between the 3rd and the 4th term. But the other thing you have to do then is to engage in mapping. Because what you also need to do in mapping is to establish valid relationships between the 1st and the 3rd term. Okay? So basically we develop, first of all, the relations between Washington and Lincoln. Then we develop the various ways in which Washington could be viewed in terms of the number 1. First president, that would suggest then that the correct answer would be 16, which would be a defensible answer here, except that doesn't turn out to be the one that's associated with this problem. But in essence, mapping is developing the relationships between the 1st and the 3rd term in that case. And finally then, once those have been worked out, what we engage in is application. We apply the principles that have been developed in the previous 3 steps to establish valid relationships between Lincoln and possible 4th terms. This latter process, the application, basically emphasizes the importance of establishing the relationships. And it builds on inference and mapping. Those are the 2 key things that are involved in that kind of a situation. What Sternberg and Gardner did in 1983 was to demonstrate that there are significant correlations in students' ability to handle inferences and mapping and application on all 3 types of tasks that are involved in solving these analogies. And in essence, Sternberg got into that because we won't be talking about it here, but he actually developed a test of intelligence based on 3 common abilities. And he applied it here, where he looked at the solving of analogies and what skills it required, as we reviewed earlier, to solve analogies, and how that bears back on intelligence. What's the correlation between the individual skills and the intelligence of people that are good at solving these types of problems? So students that are good at doing any one of the types of tasks that are involved also tend to be good in the other two. That is the three tasks that we've been talking about there: completion, analogy, and classification. Really involve skills that are very central to our tests of intelligence. And so essentially the application, the inducing of structure, involves all three of these: completion, analogy, and classification, which skills are some of the common ones that are involved in what Greeno had originally suggested as we've been looking at it here. Got another type of problem for you, and that is what are called transformation problems. Typically, these have three states that are involved. There is the initial state, which is given to you. There is then a final or goal state, which interestingly enough is also given to you. It's provided. And what you have to do is to develop a sequence of operations for changing the one into the other. And that opens up a whole new different array of looking at problem solving, as we'll see. And that is that basically the goal state is provided. And in essence, the solution tends to lead us into conducting what is called a means-end analysis. So the goal state's provided, as is the initial point and the end point, and all you have to do is develop a strategy to get from one to the other. The example that I'm going to use here involves the following, and this is a classic in the field. Well, let me define first of all what I meant. I didn't realize I added the problem here at the end, so pardon me if I'm a little bit out of order here. But in essence, when we talk about what we mean by means-end analysis, which is the last major element I'm going to present in the lecture here today, we're talking about a plan of operations used to solve transformation problems by eliminating differences between the initial state of a problem and the specified solution or goal state. What that opens up is an amazing array of information processing, if you think about it. Because given that definition of a means-ends analysis, which is a legitimate way to solve that problem, in fact, it's a recommended way, what it actually means is that you can start from the problem state and work to the goal, or you can start at the goal state and work backward to the problem state. Either way is fair, and what that leads to is a variety of strategies that we'll be looking at in the next lecture, although I'm going to have some more comments here at the moment, governing the way in which we get from the one to the other. And so the key element here is simply that means-end analysis, developing a plan, because that plan is the key thing that's involved in trying to solve this kind of a problem. If we look at, let me pose to you the particular situation. Okay? In essence, we've got a river. We can put it anywhere in the world, but given the characters of my story, we're going to put it in Africa. And in Africa, as you know, there are many missionaries who tend to be there. So we have a missionary. 3 of them, actually. We have a Protestant, a Jew, and a Catholic, if it matters. It turns out, because these missionaries are not familiar with Africa and the jungles within Africa that they're working in, they have actually hired a cannibal. Well, actually not 1, 2. Well, actually not 2, 3 cannibals to lead them. And therein is the problem, because the 3 cannibals and the 3 missionaries, as they're in their junket across the plains of Africa, have come to a river. Well, it turns out, in order to make this story complete, there is a boat available. Little crude, but it'll work. And therein is the problem. And it's really fun to try to solve this, and I'll show you some ways in which to make it even more difficult for your friends. But in essence, the rule that you have to operate with is that it is possible to get all 6 across the river, but the single rule that has to govern both sides of the river all the time is that at no point do the number of cannibals outnumber the number of missionaries. And therein is the hang-up. Therein is the problem. Okay? So how are you going to do it? One possibility is, of course, that you could put a cannibal and a missionary on the boat and have them row across, and then it would have to be the missionary that rows back. That's one possibility, because at that point you've got equal numbers. You've got 2 on the right side and 1 each on the left. The weaker member, the missionary, rows back, and so in that case the missionaries are ahead 3-2. But then you're going to face problems on the other side when you try to decide what to send over next, because if you then send 2 missionaries across, you're going to leave 1 missionary in the presence of 2 cannibals over on the other side. So that won't work. You can't start with sending a missionary and a cannibal over. In fact, to give you a hint of what will actually solve the problem is, the only thing you can actually do here to get this thing started is to put 1 cannibal, indeed 2 cannibals, in the boat. And you send both cannibals across the river. Now, if you want to get the boat back, there's only one possible solution, and that is that, whoops, how did that happen? Bizarre. Ignore those 2. I didn't program this properly. But in essence, if you look at what's going on the other side, the only way that you can solve the problem now is to have 1 cannibal bring the boat back. And the situation, ignore these 2 disrupting things here. Noise is what we'll call them. But at this point, we're fair, because we've got 2 cannibals on this side, no problem. And in this case, the missionaries outnumbered the 1 remaining cannibal 3-1, no problem. And in fact, when the, whoops, I do need to back up here. So we're going to be stuck with let me go back to where I know it'll work. I guess it was trying to get them back across that caused the problem. This is what we end up with. 1 cannibal is going to have to go back. And at this point, you're going to end up with 2 cannibals on this side and 3 missionaries on the other side. In terms of that, in order not to violate our rule that at no time do the cannibals outnumber the missionaries, there's only 1 possible combination that you can send back across the river second time. Remember, it's 3 and 2. What do you have to send back in order to preserve the rule? Go ahead.
You have to send the 2 cannibals back over.
But if you do that, you're then going to end up with well, okay, we can do that. It's a longer way to solve the problem, but you can do that. All right, so then you're going to send, the 1 cannibal brings the boat back, all 2 cannibals go over. That means 1 cannibal is going to have to come back. And that now means, I did misspeak, that now means there's only 1 possible combination that can go back across the river in order that the cannibals never outnumber the missionaries. And what would that be? That would be 2 missionaries. Because now, remember, as she just described it, we end up with 3 cannibals on one side, 3 on the other. Only 1 cannibal, since that's all we've got with the boat on the left side, can go back across, and that still preserves. Cannibals are in majority, absolute majority on the left side, and it's a 3-to-1 ratio favoring the missionaries on the right. So what that means is that the only way to balance it and get the boat back across the river if you're going to transport anybody is 2 missionaries have to row the boat across. So now you've got 2 missionaries on the left and 2 cannibals on the left, 1 of each on the right. In order to keep the balance correct, who has to row the boat back across now? Remember, we've got 2 cannibals, 2 missionaries on the left, and 1 cannibal, 1 missionary on the right. In order to make sure that the cannibals are never in a majority, the only way to do it is to divide the cannibals. Where 2 missionaries came across, 1 cannibal has to go back across. No, that won't work. What did I describe? We got to an end state of 2 cannibals and 2 missionaries. So what has to go back across is 2 cannibals, 1 cannibal and 1 missionary. Because that way you've got 2 of each on the left side and 1 of each on the right side. So 1 of each has to go back across on the boat. And therein you have done enough to be able to simply replicate that theoretically enough times to solve the problem. But you can see that the various combinations, such as the one she suggested, there are just innumerable combinations with which to do it, and it becomes an interesting mathematical problem. But in fact, when you get back to having 2 cannibals on the right and 2 on the left, you're facing the same problem again. That is, you've got to still have the same number. And so you have to follow the logic of keeping the missionaries in the 2 positions. So in that case, with 2 on the right side, 2 of each on the right side, you'd have to send 2 missionaries back across, and so forth. So that basically what makes this an interesting problem is that the redundancy of the logic that you use to get one pair across is exactly replicated to get both the second and the third pair across. But it's mathematically extremely extensive. It can be solved in as few as 9 trips across the river. But I'll challenge you to figure that out between now and the beginning of our next lecture, when we'll be looking at the other side of problem solving, which is creativity. But as you can see here, there is a substantial amount of work in investigating the various types of problems that we can talk about. We'll talk about creativity next time.